Hello everyone. So in this video session I will be continuing the topics of module 3 partial differential equations. So far we have found the formation and solution of partial differential equation. So today we will discuss about derivation of one-dimensional wave equation. Now for deriving, first we shall consider the figure. So here in the figure we consider a uniform elastic string of length L. We are considering a uniform elastic string of length L which is stretched tightly between O and Q, or O and A also you can take. This is your point O and this is your point Q. You are considering a uniform elastic string of length L which is stretched tightly between the points O and Q, and it is displaced slightly from its equilibrium position. Okay, let me repeat. You are considering an elastic string of length L which is stretched tightly between the points O and the point Q, and it is displaced slightly from its equilibrium position. Now you take O as the origin, and this OQ as your x-axis, O as the origin, OQ as the x-axis, and this perpendicular line from O as the y-axis. Okay, let me repeat. You are considering an uniform elastic string of length L which is tightly stretched between the points O and Q. Let it be your O and this point as Q. You can mark this O and Q when you write down, and it is displaced slightly from its equilibrium position. Now O is the origin, OQ you take it as x-axis, and the perpendicular this line from O as the y-axis. Now let me disturb this string slightly from its equilibrium at certain time t and release. Let me disturb this string slightly from its equilibrium position and let me release it at certain time t. Then what happens to the string? The string starts to vibrate. What we need to do here is we need to find the displacement of the string with respect to its distance and time. That is, we need to find u of x comma t, where x is the distance and t is the time. So first we need to make assumption before we start. Okay, the assumptions are, the first one here is the tension T of the string is same throughout. We are assuming that the tension of the string T, the tension T of the string is same throughout. And the second one is the effect of the gravity can be ignored due to the large tension T. Due to the large tension T, the effect of the gravity on the string can be ignored. The motion of the string is in small transverse vibration. The motion of the string is in small transverse vibration. We will see this in detail as we derive the one-dimensional wave equation. So what we are doing is, here we are considering a flexible string tightly stretched between two fixed points at a distance L apart. A string of length L is tightly stretched between 2 points A and Q. The length of the string is L, and let rho be the mass per unit length of the string. Now we will proceed with the derivation with the figure. Let T1 and T2 be the tensions at the points A and B. You consider 2 points A and B. A is of length x here. Here this distance is x, and let this distance be x plus delta x. You consider any point, two neighboring points A and B here. This is the point A. Here x is the value of x coordinate is x, and here it is x plus delta x. 2 points at a distance delta x apart. Let T1 and T2 be the tensions at the points A and B. Since there is no motion in the horizontal direction, the horizontal components T1 and T2 must be constant. Here there is no motion in the horizontal direction. So when you disturb the string from its equilibrium position and release it at a certain time, the string will vibrate in the vertical direction. So there is no motion in the horizontal direction. So the tension at this point A, that is T1 cos alpha, and tension at B, that is T2 cos beta, must be equal to some constant, say T. Tension at T, what is this alpha? What is cos alpha? Adjacent by hypotenuse. So here you can observe this is T1, right? See, T1 is, and here T is, tension is T1 cos alpha, and here it is T2 cos beta. I named it as alpha and beta. So T1 cos alpha and T2 cos beta, let it be equal to T, where alpha and beta are the angles made by T1 and T2 with the horizontal axis. Now you can observe here the tension, vertical components of tension are minus T1 sin alpha and T2 sin beta. Why here minus T1 sin alpha? You can observe T1 is directed downwards, so it is negative. We are taking it as minus T1 sin alpha. The vertical components of tension, it is minus T1 sin alpha and T2 sin beta. Here T1 is directed downwards, so we are taking it as minus. Hence the resultant force acting vertically upwards is T2 sin beta minus T1 sin alpha. So the resultant force, total resultant force is T2 sin beta minus T1 sin alpha. Now you apply Newton's second law of motion. What is Newton's second law of motion? Force is equal to mass into acceleration. F is equal to ma. So what is your force here? The total force is T2 sin beta minus T1 sin alpha. The total force is T2 sin beta minus T1 sin alpha, which is equal to the mass per unit length. The length here is, you go back and see, this is delta x, right? This is your delta x. So mass per unit length is rho into delta x into acceleration. What is the acceleration? Dou square u by dou x square. What is u now? U is the displacement of the string, and it depends on x and t. I mean to say u is a function of x and t, distance as well as time. So u is a function of two variables, x and t. So you are going for partial derivative. You know what is acceleration, right? Second derivative, velocity, acceleration. If u is a function of only t alone, then du by dt, and d square u by dt square is your acceleration. Du by dt is the velocity, d square u by dt square is your acceleration. But since here u is a function of both x and t, we are taking the partial derivative. So that's what I have written here. Rho into delta x is the mass of the element of the portion AB, right? The mass of the element of the portion AB, mass per unit length. and the second derivative with respect to t represent acceleration. Dou square u by dou t square represents acceleration. Now you divide throughout by t. What do you get when you divide throughout by t? T2 by t sin beta minus T1 by t sin alpha is equal to rho by t delta x into dou square u by dou t square. Be careful here, you are dividing throughout by t. T2 sin beta by t, or you can write it as T2 by t sin beta minus T1 by t sin alpha is equal to rho by t delta x dou square u by dou t square. When you say you are dividing throughout by t, you are dividing each of the term by t. Now from 1, T1 by t is equal to 1 by cos alpha. I don't think I named it as 1. Yeah, I named it as 1 here. T1 cos alpha is equal to t. Go back and check. T1 cos alpha is equal to t and T2 cos beta is equal to t. So what is T1 by t? When you get t to the other side, it becomes T1 by t. Cos alpha goes to the other side, it becomes 1 by cos alpha. So T1 by t is equal to 1 by cos alpha. And what is T2 by t? T2 cos beta is equal to t, or T2 by t is equal to cos beta. So substitute that here. T1 by t is equal to 1 by cos alpha. T2 by t is equal to 1 by cos beta. So you have here T2 by t sin beta minus T1 by t sin alpha is equal to rho by t delta x dou square u by dou t square. So substitute for T2 by t. What is T2 by t? 1 by cos beta. And what is T1 by t? 1 by cos alpha. So what this term becomes? Sin beta by cos beta minus sin alpha by cos alpha. Verify here. Sin beta minus cos beta sin beta by cos beta minus sin alpha by cos alpha is equal to, the right hand side you keep as it is, rho by t delta x dou square u by dou t square. Now what is sin beta by cos beta? Sin beta by cos beta is tan beta minus, what is sin alpha by cos alpha? Tan alpha, right? So this will be tan beta minus tan alpha is equal to rho by t delta x dou square u by dou t square. So verify this. Tan beta minus tan alpha is equal to rho by t delta x dou square u by dou t square. Now what is tan beta and tan alpha? Tan beta is nothing but the slope at b, and tan alpha is nothing but the slope at a. So you can go back to the figure, just go back to the figure and check. You have the point A here. You have the point B. What is the slope at this particular point A, and what is the slope at this particular point B? At the point A, the slope is given by tan alpha, and here it is tan beta. So now tan beta is the slope at the point B and tan alpha is the slope at the point A. So what is tan beta? Dou u by dou x at the point x plus delta x. It is tan, slope is nothing but the first derivative, right? Since it is a function here also, since u is a function of two variables x and y, you are taking dou here. So dou u by dou x at x plus delta x, and tan alpha also the same way, dou u by dou x at x. This is at x, that is A, point A, and this is at point B. So tan beta and tan alpha represents the slope at the point B and A respectively. So tan beta is given by dou u by dou x at the point B, that is x plus delta x, and tan alpha is dou u by dou x at x. So substitute, we will get tan beta minus tan alpha. Tan beta minus tan alpha. What is tan beta? Dou u by dou x at x plus delta x minus tan alpha. So minus dou u by dou x at x is equal to the right hand side as it is, rho by t delta x dou square u by dou t square. So now what you do is you divide throughout by delta x, divide throughout this equation by delta x, and take the limit as delta x tends to 0. Divide throughout by delta x and take the limit as delta x tends to 0. What do you get here? Limit delta x tending to 0, dou u by dou x of x plus delta x minus dou u by dou x of dou x at x divided by delta x. Okay, you divide this by delta x. First you divide throughout by delta x. What do you get when you divide throughout by delta x? Dou u by dou x at x plus delta x minus dou u by dou x at x divided by delta x is equal to rho by t delta x dou square u by dou t square divided by delta x. So here delta x get cancels, right? You are left with only rho by t dou square u by dou t square. Now you take the limit as delta x tending to 0. So limit delta x tending to 0, you are divided by delta x here. Limit delta x tending to 0, dou u by dou x at x plus delta x minus dou u by dou x at x divided by delta x is equal to rho by t dou square u by dou t square. Here no term containing x, so no question of taking limit. But what you can observe here, the LHS is nothing but the derivative of dou u by dou x with respect to x, treating t as a constant, right? This is the definition of derivative of dou u by dou x with respect to x, treating t as constant. That is dou by dou x of dou u by dou x, or dou square u by dou x square. So hence what do you have? Dou square u by dou x square is equal to rho by t dou square u by dou t square. Now this is the derivative of dou u by dou x with respect to x. Derivative of dou u by dou x, that is derivative of dou u by dou x. Dou by dou x of dou u by dou x, or can be written as dou square u by dou x square. Fine. So hence we have, go back here, dou square u by dou x square, this is dou square u by dou x square is equal to rho by t dou square u by dou t square. Dou square u by dou x square is equal to rho by t dou square u by dou t square, or you can also write it this as dou square u by dou t square is equal to, shift this rho by t to the other side, it becomes t by rho. Dou square u by dou t square is equal to t by rho dou square u by dou x square. Okay. Now what you can do is, this T by rho is a constant. This T by rho is a constant. You can denote it as another constant, say C square. If you denote T by rho as C square, what do you get? Dou square U by dou T square is equal to C square dou square U by dou X square. Dou square U by dou T square is equal to C square dou square U by dou X square, or this dou square U by dou T square can also be written as UTT is equal to UTT, and this is UXX. So UTT is equal to C square UXX. So this is the wave equation in one dimension. Remember, UTT is equal to C square UXX, or dou square U by dou T square is equal to C square dou square U by dou X square. This is your one dimensional wave equation. So this derivation is extremely important. The derivation of one dimensional heat equation and also the solution of one dimensional heat equation, wave equation, both the derivations of one dimensional heat equation as well as one dimensional wave equation. Similarly, the solution of one dimensional heat equation and the solution of one dimensional wave equation, which I am going to do in the next video session, is also very important.